tuning control method in self-driving car also, because we also train the automatic vehicle on this technique. So this is the greenhouse effect that I had mentioned earlier. The transport contains 13% of the greenhouse, and we are interested to decrease the greenhouse effects. Other energy 3%, energy supply 26%, agriculture 14%, and industry 90%, building 8%. So background and motivation, some background I mentioned earlier also, that there are advancement in automotive technology. So we are moving from and variability in dynamic responses like CF. CF is actually the efficiency of output power and input power, and eta F is the equivalent factor of the intake. Like in engine, we are intake the manifold or fuel. So mass is intake in the engine, and it is equivalent to the eta F multiplied by pressure. So it exerts, as you know that there are 4 steps occur in the engine: that intake the fuel, then combustion, then compression stroke, and then exhaust. So this will generate internal heat also, that is represented by Q. So all these factors will change the system settling time. Okay. Like the steam is stable, but the system stability will change the settling time because of some of these factors. Response types and application, importance of engine speed control. As I mentioned earlier, how much the engine speed is important in the vehicle. We are every time we are dealing with the speed in the vehicle, like we are accelerating and decelerating, so that is. And energy management and set point establishment, challenges in engine dynamics and control design, application of neural networks and control everything. So one factor I show here about the temperature, that if for different temperature like for 60, 70 and 80, and intake manifold pressure will vary with respect to the temperature. So this is one factor also I mentioned here, and my set point is 2000. So the system is stable from the initial value 1600 and 0.5 for the pressure, and 1600 rpm for the engine speed. So problem formulation is based on the previous literature review, that hybridization for energy conservation. We are interested in energy conservation, challenges in powertrain coordination and complex dynamics of the engine, uncertainties during startup operations, learning techniques for optimal control design. So this is the diagram of the engine, that we take the manifold that is represented by inlet mass m dot n, because mass is varying. So it will enter into the engine through the we are controlling it through the throttle valve. So if we control the throttle angle, then we can control the engine intake manifold or engine intake fuel. So then it will go to the compression and exhaust stroke, and the mass will come out m dot out, means m out. Okay, so according to the Newton's second law, the equation 1 is representing Newton's second law, g of theta, derivative of omega is nominal torque minus load torque. And the change in internal energy within the manifold is determined solely by the difference between inlet and outlet gas flow rate, given by ideal gas PV is equal to mRT. Okay, so if we take the derivative of this PV is equal to mRT on both sides, then we will become RT over V is the constant, and mass is change, input mass is change, output mass is change. So m dot in minus m dot out, it will be the equation number 2. And these two equations we are interested in here, like this omega engine speed, and this Pm the pressure of the intake manifold. So this is the control efficiency. F is P out over P, and that is tau omega Q on. And similarly, if the total mass of gas left in a cylinder with well-defined equivalent coefficient eta F is m string is eta F multiplied by Pm, and mean airflow can be expressed via mean value of treatment, that is m dot out is equal to eta F over 4 pi omega Pm. That is reference with this paper also. This yields a mean value representation of engine torque. Tau E is equal to eta F C F Q over 4 pi Pm, and if we substitute this tau E value in equation number 1, then derivative of omega will equal to 1 over j theta multiplied by tau e, and tau e is this one. Tau is eta f c f q over 4 pi. So this derivative of omega will become eta f c f q over 4 pi f 1 over j0 and pm minus 1 over j0, that is from equation number 1, with tau load, and there is no input in the first state. And the second state, if you put this tau e in equation number 2, this one, then it will become RT over V m dot n, where m dot n is our u is equal to m dot n. So this RT over V becomes u, and minus because of this formula, minus m dot out. So m dot out is this one, eta f over 4 pi into pm and omega, and RT over V is the constant from the equation number 2, and this RT over V will become also with the u. Okay, so now neural network control is a neural network works same like human brain. It contains neurons and the layer are in parallel mode. So it's same work like a build to acquire and preserve real world knowledge, and it enables practical application. It resembles to human brain operation as a black box model, because just as human see the environment and take action, and no need to do mathematical modeling. Same neural network take action from the output and control the input. So this is the components of neural network: neurons, synaptic weights, activation function, layers, input layer, hidden layer, output layer, and bias. Bias is like these are our state x1, x2, x3, and so on, and this will multiply with the weight plus bias. If this factor is equal to 0, then we will take bias equal to 1. So that our u should not equal to 0. And this u will pass again to the activation function. Activation function can be like sigmoid, then hyperbolic, relo, like this. When we pass this through the activation function, then we will get some output, and this will be our error from output minus input. And we will use loss function like this. I say error and optimizer. We will use some optimizer to decrease our output value to the 0. And learning rate. What is learning rate? Actually, learning rate is in the next slide I will show. There are two modes of learning: online learning and offline learning. And this is the learning rate. Delta W is equal to minus eta with respect to error. And we want to reduce this error so that our weight will be trained through the learning rate that is occur between 0 and 1. So eta is here learning rate. And if our error increase, then we will change our eta. We will change our learning rate value. It lies between 0 and 1, like 0.1, 0.2, 0.3, like this. And in online learning, we are taking the difference between input and output values, and we are calculating the error, then we will minimize it. And in offline, it's same like pattern by pattern methodology, where the primary objective is to discover the weights and minimize the square of the equilibrium norm in the vectorial disparity. And in offline learning, we are minimizing the cumulative error, overall error of the system. Like what is the cumulative error? Then it will pass again to the system, and we will adjust the weight of the system again to reduce this error. So that's why it is called back propagation, because we are moving back again for adjusting the weight. And feed forward, we will initiate some initial value, some random value of to select the weight of the neuron, and we will move forward. So this is the back propagation, and we will come as we will initiate the weights with some small values, random values. Then we will select the state x of k, t of k, and then we will use the error from this method w multiplied by o, where o is error. So pi minus oi means input minus output. This error we will minimize it through the some optimizer, and we will optimize our weight through learning rate eta. For L is equal to L, so 1. How much layer we have, and each neuron contain weight, so we will reduce every weight. And repeat the process beginning from step 2 with another example. Then when our error becomes 0 or less than 0, then we will stop. Okay. So now for this system, I designed many neural network but I here mention only the 11 best one because other error that is was greater than 0. So for these layers, my error is like 10 to the power minus 7, 10 to the power minus 6, 10 to the power minus 2, and 10 to the power minus 2. But here one thing I want to mention that among these best design of the neural network, I select network number 9. Why? Because it contains only 4 layers, and first layer contains 10 neurons and other layer only 1 neuron. Okay, so the size of the layer is minimum and the number of neuron is minimum. So cost will be minimum. We will also take the cost. We are not interested only in to reduce the error. We are also interested in the cost. So if we take the network 1, it has the same 10 to the power minus 7, and it also has the same 10 to the power minus 7. But the difference is that it has 10 number of layers and each layer contains 10 neurons. So it will has high cost. And if we change the activation function like secure like number of layers are same, but if we change the activation function, then array will also affect. Like here the error increase 10 to the power minus 2 from 10 to the power minus 7 to 10 to the power minus 2 if we use this activation function. So how we will design the controller or neural network, like it's out xn, let's say input, and yn is our desired. So omega minus omega d, we will omega d means desired omega, and we will control it through the gain 1 over k1. We will pass state x1 is what our state omega, and x2 is our pressure pm. So we will adjust the gain of the controller k1 or k2, so that we pass this error to the controller gain, and then from there we will calculate the error, and through this ARM based algorithm the controller will automatically self-tune itself for the desired requirement of the engine. It will reduce the error until it will tune the system until the error is become 0. Okay, so for RQ controller design, we know that we are calculating the K from the Q and R matrix, and that is Q1, Q2, and R, and we will minimize this cost function J in the LQR method. And as I mentioned earlier that LQR, as from its name, it's used for linear system. So we will first linearize the system, then if we do mathematical modeling. But if we are interested in here, then in the stability region, we will not require such a mathematical modeling. And for PID, we all know that PID contains proportional, integral, and derivative controller. Proportional is same like current error. If there is no steady state and there is no overdamping, then we will use proportional proportional controller. And if there are some steady state, then we will increase the integral constant. And if there are some overdamping, then we will reduce the overdamping. So for sliding mode controller is one of the robust non-linear controller used in the used for the non-linear system. It has 3 components. First, we will design a sliding surface, and then we will force the state of the system to follow the trajectory of the sliding surface. We will force all the states to follow the trajectory of the system. So this is used in the research very abundantly because of its robust nature, and it has some chattering effect like plus minus chattering effect, and we will use this from signal function. So for this system, I designed this sliding surface, that is super twisting sliding surface for this controller, for this engine. So S is equal to A x1 minus xr. X1 is my state, that is omega, and xr is the reference, that is I take 2000 here, plus x2 b multiply absolute of x2 into gamma. This is sliding surface for the x1, and accordingly I designed the super twisting sliding mode control law that validate u is equal to v over rt multiply 1 over x2 minus k1 multiply by sliding surface s minus k2 multiply by signum of s. And this signum is actually used for the control of chattering effect of the sliding surface, where a, b, and gamma are the tuning parameters for the super twisting sliding surface, and k1 and k2 are the proportional gains in the control law. We will adjust this control through this gain. Okay, for results in simulation, we perform LQR, PAD, and SMC controllers through a conventional method, and then we apply neural network upon it, and directly just input and output we did through neural network, and we will show that how it train and how it give us the result. So this is the engine specification that I use in the simulation. That fuel cylinder type is 4-cylinder air type, and displacement is 1.97 liter. Maximum torque is 142 Nm, and maximum output power is 72 kilowatt. And nominal torque is this one. Nominal power consumption 250 kilowatt, and internal moment is. So this is the specification of the engine. So ANN based LQR, I perform two training for the low range of settling time and for the high range of settling time, and I justify my validation that for like if I take the value from 0.4 to 0.04, then it show like error of maximum 4%, that is acceptable, 3 to 4%. And I also test upon the higher gain, that is from 3 to 0.5, and for this gain ranges it also show error, maximum error 4%. This is the trend of gain versus settling time, that how it change. Like it is more sensitive with the passage of gain. If you increase the gain, then settling time also affect. So this like if we have system like this, then our neural network will be well trained, will be trained in a good way, because the relationship between settling time and gain is varying with the passage of time. But sometime in PAD I will show that there is minimal deflection of the settling time when we increase the gain, but the settling time remains constant. So in that case, the neural network will not well trained. So this is an based PID, and in this case you can see that the error is acceptable, but it is not well trained or not well showing values at some points. The reason behind this, as I will mention in the next graph, that for this graph, the behavior of the gain versus settling time is not sensitive, and for this, for higher gain, it's performed good. And also about PID, we also know that if we use PID for the very small fluctuation of the throttle valve, then it does not give us a good response. So that's also the one reason, because in the next graph you can see here that in this you can see abrupt changes between settling time and gain, but in the figure 11a you can see that from for lower values below 0.5, if we increase the gain, then the change in settling time is very low. So that's why for low values, in the previous this shows some not good training. Okay. And ANN based SMC, as I also mentioned earlier, that sliding mode controller is gaining most popularity in the research because of its very robust nature, and it show in the lower and upper values very good training. Okay, I check for different values in the lower and higher, and you can see the higher gain is also maximum 2% error when we are dealing in the low range of the settling time. And in the higher range, it show only 1% error. Like we are getting our desired values very closely. So it has the effect of its variation is like this for the lower and higher gain. And conclusion, as your controller, it has integration of ANN for setting the prediction based on gain parameter. So noteworthy results across both lower and higher gain ranges we obtain, and promising accuracy in lower range with minimal errors. It also gave promising accuracy in the lower range also. And PID show valuable performance in lower setting time with acceptable error threshold, and certain gain values leading exception and slightly elevated error percentage. Like for certain gain values, that leads to the exceptions that I showed in the previous slide, and slightly elevated error percentage. And in an SMC controller, that is relatively higher cycling time ranges, and it's relatively show good performance in the both low and higher ranges. So that was the